symmetry, symmetry and symmetry. We'll be talking about symmetry only today. Gauss theorem is universal. Universality of Gauss theorem I have mentioned already. Today we'll see in practical application in finding electric field due to a continuous distribution of charge, because due to a point charge I showed you one example yesterday. I'll be doing with continuous distribution of charge and how easily electric field can be determined, strength of electric field with the help of Gauss theorem, that I am going to discuss today. Hello everyone, MK here. I'll be discussing Gauss law application today. Only application of Gauss law. So many applications are there. In the first part of today's session, I'll be discussing the application which you need for your board examinations, and the rest will be for entrance examinations. Stay tuned till the end of this session. I'll remind you important information which you have learned in the first session on Gauss law. The cylindrical, planar and spherical symmetry. I was talking about this in the first session also. Spherical symmetry you already have seen, where due to point charge the strength of electric field is proportional to 1 by r square, isn't it? E equal to q by 4 pi 0 r square. Due to spherical charge distribution, also E proportional to 1 by r square. So here charge density depend only on the distance from central point, and electric field due to spherical symmetrical charge distribution will be proportional to 1 by r square. Got it? Am I clear? So E is proportional to 1 by r square. What is cylindrical symmetry? Charge distribution is cylindrically symmetric if the charge density depend on distance from the central axis. Probably you have seen this, you have calculated this. Yes, we did it. When you are finding the strength of electric field due to line density of charge, we have done it with the help of Coulomb's law. If there is line density of charge infinitely long, then at a distance r, the strength of electric field, as I remember it was, if lambda is the line density of charge, then E equal to lambda by 2 pi E0 r. Here also it depend on the distance, but this time distance from the central axis. Central axis case will arise in case of cylinder. Do you understand? So this spherically symmetric was possible for a point charge. At certain distance r, strength of electric field is proportional to 1 by r square. If you go far away from this charge, then also it is inversely proportional to square of distance. And due to this linear charge distribution, and we will find more cases here, due to cylindrical charge distribution, hollow or solid cylinder, it doesn't matter, E is given by, E is proportional to 1 by r. In this session, our aim, what is our aim in this session? Do you know? Our aim in this session is to avoid complicated integration to find the strength of electric field due to a charge, continuous distribution of charge, etc. Okay? What is planar symmetry? Planar symmetry you haven't seen. Charge distribution is said to be planar symmetric if the field due to charge distribution is a constant. So in spherical case proportional to 1 by r square, cylindrical case proportional to 1 by r. In planar case, we'll see that E is equal to a constant. Okay, I'll give you many examples on these three symmetry in electrostatics. We'll start one by one. Okay, so this what I told you, I have set some example here, but this is already told. Spherical symmetry observed in case of point charge, uniformly charged spheres. Cylindrical infinite line charged cylinder or thin wire which is charged, long straight wire which is charged. Planar system will be doing one application or two applications. Let's see. When there is infinite plane sheet of charge. Okay. Then, what is the link between Gauss theorem and symmetry? Already mentioned, Gauss theorem is most powerful when applied to system with high symmetry. Last session only I told you, we don't apply Gauss theorem always. If you find symmetry, we will use Gauss theorem. Why? Because symmetry will allow us to assume a uniform electric field over the Gaussian surface, simplifying the flux calculation. Our main aim is to calculate flux calculation. Then, in addition to that, electric field strength can be calculated. Yesterday I showed you one example, charge distribution case also, how Gauss theorem helps. It is a nice example, I told you to remember. Now, what is a Gaussian surface? This also we have used, hypothetical closed surface in space through which flux of electric field is calculated using Gauss law, that is called Gaussian surface. Okay? Characteristic is what? Surface will be chosen in such a manner that the symmetry of the problem is there, then only. Can be spherical, cylindrical or planar depending on the charge distribution. So when you are going to find electric field due to cylindrical charge distribution or a infinitely long charge thread, cylindrical, that charge is distributed on a plane surface, there will be planar symmetry, and spherical when there is point charge or hollow sphere or solid sphere, whatever. The field is proportional to 1 by r square. If you find these symmetries, then calculation will be very easy. And another thing, you should remember, this I have stated in the guideline. What is the guideline? When you are going to find electric field due to a charge distribution, you find the symmetry. What symmetry is there? Spherical, cylindrical, planar, you find it first. Now, when you are going to apply, you need to check another point. You must ensure that electric field is either constant or 0 over sections of the surface. Then simplify the calculation, choose a surface where the dot product is easy to compute. E dot dA, easy to compute. I am going to show you with example. I will be showing you these three examples first. Electric field of an infinite line charge. Then electric field of conducting cells or spheres. Field due to an infinite plane sheet of charge. This derivation will help you to understand Gauss law. These derivations are important. Derivations for board exam. Okay, these three we are going to do one by one. Let us start with electric field of infinite line charge. This is of infinite line charge. Imagine it is finite. You think that it is infinitely long charge thread. It has line density of charge which is given by lambda. Lambda equal to line density of charge. Okay. We have to find strength of electric field at some distance P away from it. At some distance R away from it. P is the point. What you did in Coulomb's law, I just remind you. In Coulomb's law, you used to divide into infinite number of parts. One elemental part is there. This is one elemental part. Symmetry is there. Another elemental part is there. Or you forget Coulomb's law now? Can you forget? No, in this chapter only. So, due to this elemental portion, electric field here at the point P will be directed this manner. Okay, let us take this as DE1, and due to this elemental portion symmetrically opposite, the direction of electric field this way. So resultant electric field due to DE1 and DE2 will be this manner, and this field is proportional to 1 by R, isn't it? It depends on the distance. Go far away from the distance, then strength of electric field will be reduced, isn't it? Now, how to find the strength of electric field at the point P at a distance R from the charge thread? This we are going to discuss. I told you, if you find symmetry, what symmetry is there? It depends on distance. It is proportional to 1 by R. So there will be cylindrical symmetry. Okay. Cylindrical symmetry is there. If the strength of electric field is inversely proportional to R, then cylindrical symmetry is there. So for that, we will be taking the Gaussian surface, which will enclose the charge, thread, and it will be symmetric. Let us see. So we have taken the Gaussian surface this manner, which is a cylinder. Because cylindrical symmetry is there, we will take the Gaussian surface through the point P, which is nothing but a cylinder. Okay. So to find the strength of electric field at any point on it, what you will remember? First we have to see whether symmetry is there or not. It is proved that symmetry is there, and that symmetry is cylindrical one. That's why I have taken the Gaussian surface this manner. Okay. Also it is proved that strength of electric field is proportional to 1 by R, and direction of field is perpendicular to the Gaussian surface. This is our Gaussian surface. This cylinder is the Gaussian surface. Okay. We are going to find strength of electric field at any point. It is proved that symmetry is there and the strength of electric field is radially outward, E. Okay. If I have taken a small surface area of the cylinder here at this point, then obviously area vector is perpendicular to the curved surface. So E and ds have the same direction. Am I correct? E and ds have the same direction. So now we can use Gauss law. Lambda is the line density of charge, already mentioned. This is infinitely long, its length you cannot consider. This line density of charge means for this thread only, lambda is the line density of charge. The cylinder's radius going to be equal to R, the distance of the point where you are going to find the strength of electric field. And length of this cylinder, you take L. Length of infinitely long wire no one can say, but this one you can say that Gaussian surface, it is finite in size, Its height is L and radius is equal to R. Clear till this? Now you have to find the surface. How many surfaces are there? You can see that there are three surfaces. This S1 is a surface, S2 is this end cup, another surface, S3 is the other surface. But lines of forces due to this charge distribution, all lines of forces are radially outward, isn't it? Lines of forces are radially outward. All lines of forces are radially outward. So on this surface S2, if you have taken a small area on this surface, then area vector directed this way, it is ds2. But electric lines of forces are going this manner. So electric field and area vector making an angle what? They are making an angle which is equal to 90 degree. Am I correct? Similar is the case for this surface. Here also, if we have taken a surface, small surface, ds3 at the end cap, then ds3 directed this way, electric field strength directed this way. So angle between them is again equal to 90 degree. Am I correct? Now let us remember the Gauss law, that is phi is equal to surface integral of E dot ds, isn't it? So here in our problem, this is going to be what? This is the surface integral on all the surfaces. So let us find it, the value of phi on the surface S1 E dot ds, on the surface S2 E dot ds, on the surface S3 E dot ds. Alright. In case of S1, electric field is along area vector and E has the same value. So E on the surface, we just take E, it will be E ds cos 0 degree over the surface S1. Here it will be E, this is what? This is cap 2, I mean cap 1, whatever, these two end caps. So E ds cos 90 degree, angle is 90 degree. So even on S2, if you find the value of this integrand, it will be 0 because cosine 90 degree is there. Similar is the case for surface S3. This is also EDS cos 90 degree. So the value going to be over the surface is EDS. Now by symmetry, that's why you are using Gauss law, no Coulomb's law, Gauss law. Every point on this imaginary cylinder, electric field strength has the same value. So you can take E outside ds. ds is what? That total surface area, it is 2 pi RL. So phi equal to E into 2 pi RL. Clear? So phi you have calculated by formula. It is E dot ds, which you have done in past session, that by the use of this formula flux can be calculated. In Gauss law, what you do, you use the law now and compare with this so that E will come out. But phi out phi out total normal induction or total outward flux, whatever you say. This is going to be what? The strength of electric field, magnitude same at this point E. Anywhere you go on this surface, it is E only. On the curved surface, it is E into area. That we have taken already. So this time phi out, you have to calculate by Gauss law. That is Q enclosed by E0. How much charge is enclosed over there? Let us see. How much charge is enclosed? It is Q enclosed divided by E0. How much charge is enclosed? Line density is lambda and length is L. So charge enclosed will be L into lambda by E0. This is line density of charge. No, cylinder is Gaussian surface, but this one line density. Per unit length charge is lambda. So over the length L, how much charge is there? L lambda. Now compare these two. This is also phi out. As it is coming out, this is also phi out. Now compare these two phi's. That E into 2 pi RL equal to L into lambda by E0. So E equal to lambda by 2 pi E0 R. See how easily can be determined here. We don't need any integration. Okay, only by Gauss law. Why? Only by Gauss law? Because Gauss did the integration part for us. Okay, we are taking the help of the theorem because of that. Theorem proof is not there in the syllabus. I told you, you have to do it by vector calculus. You need to know only application. Symmetry and symmetry. This is the beauty of Gauss law. When there is symmetry, we can find electric field at ease with the help of Gauss law. So in case of sphere, if the sphere is charged, there are two types, no? One is solid one, the other one is hollow. In this context, I'd like to say that if there is a solid conducting sphere or hollow sphere, in the sense of charging there is no difference. Because if it is conductor, if you give some charge anywhere in its volume, it will appear at the surface. Okay? Inside there is no charge, so charge will appear on the surface. And we are going to find the strength of electric field due to this sphere. Its radius is equal to R. No charge reside inside. It will lie in the surface. So this case may be due to a conducting cell or a conducting sphere. Charge will reside on the surface only. Charge resides at the surface only, isn't it? So if it is not clear from this diagram, I have taken the 2D view here. This one has radius R. No charge will reside inside the sphere. We have to find electric field due to this charged sphere. Okay? Charge resides on the surface only. How to find electric field and where to find? Symmetry is there. That spherical symmetry. Gaussian surface will be spherical always. Okay? If we enclose this one, I mean the whole sphere, the charged spherical shell, then electric field will be proportional to 1 by R square. Or it decreases with the distance. Okay? So, we'll be taking the Gaussian surface always to find the strength of electric field. Only thing you need to assume the surface density of charge. This time not line density, there will be surface density of charge. surface density of charge B is sigma. So if a charge Q given to this, radius is R, so Q will be given by sigma into 4 pi R square, isn't it? How to find strength of electric field inside, outside of the sphere, that I am going to discuss. Let us find the electric field inside the sphere at a point P like this. So spherical symmetry, we need to draw the Gaussian surface like this. A concentric spherical cell. Okay. This concentric spherical cell has radius smaller. And according to principle of charging, charge reside on the surface only. So if I say that strength of electric field at every point on this imaginary sphere, because spherical symmetry is there, E in, that is perfect. But E in will be 0 inside. Why? Because the Gaussian surface encloses no charge over there. Isn't it? Charge will decide on the surface only. I showed you charge resides on the surface. So if the point P be inside, then phi will be equal to E in dot ds. There is no problem in it because it is perpendicular to the surface of the sphere only. So E in and ds have the same direction. Next step only you can write it is E in ds. But phi is what? Phi out. Phi out equal to 0. Because Gaussian surface encloses no charge. If it doesn't enclose any charge, then outside flux will be 0. So therefore, E in into ds is equal to 0. Now E in will come outside, ds integration is what? 4 pi r square. So E in will be equal to 0. Clear? Inside the charged spherical cell, electric field is 0. Let us find its value. Same charged sphere, sigma equal to q by 4 pi r square. We want to find strength of electric field outside it, outside the charged sphere. We need a Gaussian surface. Spherical symmetry is there. If you want to find at any arbitrary point outside the sphere, you need to enclose it first. Okay, this is the Gaussian surface. This Gaussian surface has radius equal to smaller. And why this one Gaussian surface? Because spherical symmetry is there and at any point on this sphere by symmetry, same electric field exists. So this is the original sphere. Electric field due to which you are going to find at the point PC, an arbitrary point P. So Gaussian surface is this one. This is Gaussian surface. It need not be a conductor. It just has spherical shape. Only lines of forces can pass through it. So what we will do there, and it is ensured that electric field has same value. Spherical symmetry is there. You will take an arbitrary point on it. There, area vector perpendicular to it, ds. Electric field also radially outward. So E also has the same direction as that of ds. Okay. And this is the case for all points. If you take any small surface here, field is outside, radially outward, and area vector also radially outward, angle between them equal to 0 degree. So to find the strength of electric field, you take the help of Gauss law, But before that, we just go for calculating phi out. Strength of electric field remains the same. Magnitude remains the same at all points. And surface area is 4 pi r square, this time smaller. So phi out will be electric field into area, that is 4 pi r square. If you say that no, I'll calculate this one by this surface integral, no problem, you do it. Be clear in your step. It will be E ds cos 0 degree. With angle between E and ds, I have already explained, is equal to 0 degree. So E will come out S, which is given by E into 4 pi r square. But this is not the surface area of the inner one, it will be outer one. Outer one has radius smaller. Smaller is variable over there. So take that only, E into 4 pi r square. Clear? So phi out equal to E into 4 pi r square. By Gauss law, what will you get? Phi out by Gauss law formula, Q enclosed divided by epsilon 0, that is E into 4 pi r square by E0. But this time, wait a minute, this is not E into, Q enclosed will be given by surface density. No, surface density of charge is sigma. We have taken sigma equal to Q by 4 pi 0 r square. So Q enclosed going to be equal to that sigma multiplied by what? Area. Area of this portion is 4 pi r square. So just to compare these two. Therefore, E into 4 pi r square, sigma into 4 pi r square, that divided by E0. So E going to be what? Sigma into r square by E0 r square. Okay? So E is proportional to E out, better to say E out is proportional to 1 by r square when r is greater than r. If r is equal to r on the surface, you got this one E out. E in already we have done. E in is what? 0. But now I want to calculate E on surface. E surface means for r equal to r, you just substitute sigma r square by E0 r square. The value is sigma by E0, E on surface. Alright? It is a constant. This is equal to a constant. By remembering these three facts, we can easily draw the graph of electric field versus distance. Inside, what is the strength? Inside, the strength is 0. Outside, up to r, from 0 to r, it is constant, sigma by A0. No. Inside any point you take, it is 0. But outside, I mean, on the surface, it is sigma by A0 constant. And from there, sigma by A0 r square by r square, r goes on increasing. So E falls out rapidly. So the graph going to be like this. If we take E along y-axis and r along x-axis, the graph will be like this. Up to r equal to r, no electric field. Just less than r, no electric field. This part is r less than r, no? After that, at exactly equal to R, the electric field is, wait, let me use different thing for this. Just a minute. So this is for R equal to R, it is sigma by E0. This portion, sigma by E0. This is for what? This is for R equal to R. We did it here. And for R greater than R, it goes on decreasing. Here, E out is going to be proportional to E out proportional to 1 by R square. It means it falls rapidly. The graph will be in accordance with these three parts. At this part it is constant and then it is goes on decreasing rapidly. Just a minute. Just a minute, because this graph is showing almost straight line. That is not the case. It will fall rapidly, but not like this. This is going to be like this. Okay? Like this. So up to R equal to R, this is equal to 0. E equal to 0 here. From 0 to R. At this point, E equal to sigma by E0. And then E is sigma R square by E0 R square. It falls rapidly. That's why it is falling like this. You want to see the graph? It's falling like this. Clear? So electric field due to charged spherical cell is done. And one very important concept, but idea we get here. What is that? If we are not putting the value of sigma, phi out, see in our calculation, phi out is what? Q enclosed by E0. We are not planning to put the value of Q enclosed. Phi out is what? E into 4 pi R square. Therefore, E equal to Q enclosed by 4 pi E0 R square. Clear? So what does it mean? It means that the whole charge, this R is what? Distance of the point P from the center. And this expression is like what? Electric field due to point charge Qn. Where is it situated? Not on the surface. We can imagine that it is situated at the center. So in this case, the sphere behaves like what? The sphere behaves like a point charge placed at the center of the sphere. Alright? So one can assume that charge is concentrated at the center of sphere while calculating electric field due to charged sphere. Clear? Now let us go for planar symmetry. This was spherical symmetry. First one was the first one. That have I drawn the graph? Let me check once. Oh, I forgot. Here graph is very easy to plot. You can do this without any trouble because E is proportional to 1 by R square. That electric field is directly proportional to, inversely proportional to the distance from the charge. So situation going to be like this. Symmetric about both the axes. This is the graph of E proportional to 1 by R or E equal to lambda by 2 pi 0 R. Clear? This is infinite plane sheet of charge. Although it is looking finite, but actually plane sheet has no thickness. It can extend up to infinity. Both the way, it has no length and breadth. Length is infinite, breadth also infinite. We want to find electric field due to such a plane sheet of charge. And we are going to prove that it is independent of the distance. Okay. So what kind of Gaussian surface you will take so that finding electric field at a point will be easier. Suppose in front of it there is a point like this P. Here we want to find electric field strength. How to find? We have to draw a cylinder. Why cylinder? Because you cannot cover it by any finite object. What you will do to find the strength of electric field here? If you take the Gaussian surface as a cylinder, then it will penetrate. It is independent of distance. That also can be proved. Okay. So let us draw the Gaussian surface here. So I am suggesting the Gaussian surface this manner, which is a cylinder. To find the strength of electric field at the point P, we are taking this cylinder as the Gaussian surface. To explain this thing, I have taken the help of this three-dimensional diagram. Okay. Always you cannot realize that three-dimensional concept here. That's why I have taken this thing. That plane sheet of charge is there. Its surface density is given, that is equal to sigma say. We want to find the strength of electric field at this point, or at this point, whatever. That diagram, same concept I am going to explain here. And let the area of cross section of the cylinder be equal to A. Then this Gaussian surface, which is a cylinder, it will enclose some charge from the surface. How much? That will be equal to the charge enclosed in its area of cross section, you understand? If the surface density of charge is sigma, charge in this portion is sigma into area. Am I correct? It is sigma into area. Why did you say that? Because A is the area of cross section, which is equal to pi r square. I did not take pi r square over there, just simply writing it is A. So A into, if the surface density of charge is sigma, at this portion how much charge is there? This is going to be sigma into area. So Q enclosed, and due to this charge, the strength of electric field, direction of electric field will be this way for the left cap, for right cap this way. Okay. All the lines of forces will be radially outward, so it will be along the direction of end cap. If we take a surface here, say, if we are taking a portion of the Gaussian surface, then what is the direction of electric field? Due to this, the strength of the area vector directed this way, ds vector directed this way, you know. But electric field is radially outward. If we draw the direction of electric field, it will be directed this manner. Okay, from the plane sheet away from the sheet. So what is the angle between E and ds? That is 90 degree. So d phi this time going to be equal to what? D phi equal to, d phi in this case we will find on the surface, and d phi will, so this surface is S1, S2, and say this one is S3. Okay. So if we want to find phi out, that you obviously have to take surface integral of the whole surface of the cylinder, isn't it? That will split this one as surface integral of S1 E dot ds, okay, plus surface integral of S2 E dot ds plus surface integral of S3 E dot ds. Am I correct? So it will be through the end cap only. E into A, that flux will go perpendicular to the end cap. Here also E into A will pass through this end cap perpendicular to it. E multiplied by A. But this way around the curved surface, it is not there. Curved surface area we have taken S3. So as angle between E and ds equal to 90 degree, this thing will vanish. Why this one will vanish? Because E and ds, E perpendicular to ds. That's why this will not exist. Clear? Now let us find E dot ds for this one. That S1 E dot ds is going to be what? Radially outward perpendicular to the end caps. You can see the area vector directed in what direction? Area vector directed this way only. So this is given by S1 E dot ds is given by, this is same as S2. S2 surface integral of, they have the same value. So it will be E ds cos 0 degree. You will come out integration of ds. ds is what? E into E. The area of the end cap. Similar is the case here. So if we want to find phi out, this is going to be what? This is going to be due to S1, due to S2, this part is 0. But S1, S2 same. So it will be twice E into A plus 0. Clear? But phi out by Gauss law is what? We have to compare. We find it by formula and then we go for Gauss law. That is, but by Gauss's law, phi out equal to Q enclosed by E0. How much charge is enclosed over there? This portion, sigma into A. Both the way, it has no thickness. So from this side if it appears sigma A, from that side also it is sigma into A. Clear? Now compare these two. So phi out, if you compare, what do you get? Comparing 2EA to E into A is what? Sigma A by E0. So E is equal to what? E is equal to sigma by, take sigma by 2E0. Clear? So electric field we got sigma by 2. So due to this plane sheet of charge, you can see that strength of electric field is independent of what? Distance. If you write E by using vector notation, it will be sigma by 2E0. Suppose this is along Z axis, K cap, positive direction, it will be minus sigma by 2E0 K cap This is for what? This is for along z axis, z greater than 0, and this is true for z less than 0. Problem arises if it has finite thickness. Then how do you find it? This one has finite thickness. I'm just drawing it again. This one is finite thickness. Finite thickness means you have to modify this part. You said that charge enclosed will be sigma A by E0, but when it is finite thickness, then charge will reside on left side as well as on right side. So phi out, if the plate has finite thickness, then phi out is going to be Q enclosed by 0. Two sides of Gaussian surface responsible. So it will be sigma A. I mean, from this side if you see, it is appearing sigma A. From other side if you see, appearing sigma A. This sigma is different from the previous ones. So it will be sigma A plus sigma A by E0. 2 sigma A by E0. Clear? But phi out, theoretically what? Phi out twice EA plus EA. But phi out equal to twice EA. Therefore, twice EA, you just compare twice EA, I mean this part with this part. So twice EA equal to 2 sigma A by E0. So E is given by sigma by E0 if it has finite thickness. So it is quite obvious, it is in both the cases independent of distance. And one very important thing, the derivation so far we have done, that all required for your board examinations. Coming with some problem where we will apply Gauss law, but as theory it may not be asked in board paper. Clear? Thank you for staying with me till the end of this session. Next class will be on Gauss theorem part C. We will be discussing many important problems over there one by one. Wait for that. Thank you.